welcome to Lecture 4. Today we are going to be talking about the Jovian and Terrestrial Planets. This means we're going to be talking about our inner and outer solar system. So let's go ahead and jump right in. So we're going to start with the inner solar system, which is where we're going to find the terrestrial planets, which are our most Earth-like planets. The terrestrial planets focused on the 4 planets of the inner solar system: Mercury, Venus, Earth, Mars. We will cover today Mercury, Venus, and Mars, as we've already talked about Earth. Our topics are going to cover the planetary body, their interior, rotation, and atmosphere. Let's start with Mercury. The surface of Mercury is covered with scarps, craters, lava flows, and basins. The scarps are cliffs that formed where the crust has shifted and can be up to 3 kilometers high. They cut through craters and so have formed after impacts occurred. There is cooled lava filling old craters and much of the surface, and in some areas there appear to even be volcanic vents, showing us that Mercury was once volcanically active. The largest crater on the surface of Mars is Calorus Basin, which is 1,500 kilometers in diameter, which indicates that it was in fact a great impact. And we can tell this because there are mountain ranges surrounding it, and the shock waves from it actually travel to the other side of the planet, forming this hilly surface. Impact craters are all over the surface of the planet. However, walls are not very steep because of the planet's gravity, which is about 2 times that of the moon. Its rotation does have a wobble, and it has an elliptical orbit around the sun. The wobble is important because it tells us that Mercury still has a semi-liquid core. Interior observations indicate large iron core beneath a silica-based crust. This is primarily based on Mercury's density of 5.4 kilograms per liter. It's very slightly different in temperature for rock and iron condensation, 1400 Kelvin versus 1300 Kelvin, which wouldn't explain an iron-rich Mercury. Therefore, we can assume it must have had a thicker crust at some point, and that an impact must have blasted it off, leaving, the planet with a SiO2 mantle and iron-rich core. This would explain its more elliptical orbit as well, and the core appears to be molten as it has an amount of wobble as it rotates, which is affected by the gravity of the sun. It shouldn't have enough heat from the sun itself alone to keep it molten, and so astrologists theorize sulfur must be part of the core as it lowers the melt temperature of iron. A molten core would explain its magnetic field, even though it's only 1% that of Earth. So to look at a picture of Mercury in cut, you can see that it doesn't really have much of a mantle. It has crust, and inner core, and outer core. And so what scientists believe happened is that while it was still young, there was a huge impact, probably with another protoplanet, that wiped off its outer crust, leaving its mantle actually exposed, which is pretty cool. Mercury's rotation is very, very, very slow, about 58.656 Earth days. The rotation is 2/3 of its orbital period of 87.969 Earth days. Why is it so slow? It's actually due to the sun's tidal force. It hasn't completely been tidally broken into a synchronous rotation, and due to its elliptical orbit, it never will. However, its speed changes as it moves around the sun in accordance with Kepler's second law of planetary motion. While it's never fixed to having one side permanently facing the sun, Mercury's spin instead has slowed to 2 side faces the sun on the one approach and the other on the next closest approach. This is called a tidal lock. This means Mercury's day is longer than its year. So basically what happens is you have a sphere, and as it goes around, one side faces it, and then as it goes around, the other side faces it. So it takes about 176 days to have successive noons. There is an odd effect due to its rotation that causes this longer day. When it's at perihelion, or when it's closest to the sun, which is when it's going to move quickest, its orbital speed will be fastest for 8 Earth days. Its speed will override its rotation, as in it doesn't rotate fast enough. And so the result will be the sun will come up in the morning, essentially, reach about noon, and then go backwards. So it goes east-west, then, after 40 days, when we have the 8-day speed occurrence, backwards, west to east. And then after that 8 days pass, back east-west. In some locations, the sun rises slightly for several days, then dips below the horizon to rise again to complete the long day. Can you imagine your days having 2 successive noons? I think that would be pretty crazy. Atmosphere on Mercury? Not really. And this is because the temperature is quite extreme. It's too close to the sun, so any gases that Mercury would have captured would have quickly been burned off. And due to its low gravity, it has a very low escape velocity, meaning that even if the sun didn't burn it away, the gases would have escaped on their own. Temperatures range from 80 Kelvin at night to 710 Kelvin at noon at the equator. 710 Kelvin is only at the perihelion. When it's at its farthest point, the highest temperature is 580 Kelvin. No atmosphere, again, remember this, no atmosphere on Mercury due to the sun's heat and low gravity. However, cool fact, there is ice at the poles of Mercury, which is most likely due to comet impacts. Next, we're going to move on to Venus. Venus has an atmosphere that is 100 times more massive than Earth's. 100 times more massive. That's pretty big. It's pretty thick. 96.5% of that massive atmosphere is carbon dioxide, versus Earth primarily being nitrogen-rich. It also has 3.5% nitrogen and trace amounts of water and other gases. Venus has lightning storms, but no rain. The clouds are made of sulfuric acid, which cover the planet permanently, and we cannot see through it. Evidence shows that below the clouds is clear, and some sunlight does in fact get through. The atmosphere exerts a pressure on the surface 90 times that more than that of Earth's. This is equal to the pressure we would feel at 900 meters of water. For those of you who like swimming, we've all gone to the bottom of the pool in the 12-foot area. We've all felt that pressure on our heads and in our ears. Imagine that being 900 meters deep instead. Venus is also incredibly hot. It is 750 Kelvin, which can melt lead, and only cools by a few degrees at night. It is with Venus that scientists use the term runaway greenhouse effect, where the high temperatures increase this effect. Carbon dioxide in the atmosphere allows for sunlight to enter the atmosphere and warm the surface, but it also prevents much of the infrared radiation to escape back to space, keeping the planet very warm. On Earth, there is less carbon dioxide in the atmosphere, so it's just a mild effect. But on Venus, since it's 300,000 times more carbon dioxide than on Earth, we have a much stronger effect. So the surface is hotter than Mercury. Why? Well, let's pretend it was Earth. If this happened on Earth, our oceans would heat, where we would get this runaway greenhouse effect, which means that more water vapor will be released. And water vapor is actually a greenhouse gas, which will make it hotter, which makes more water evaporate. And so then what happens is, believe it or not, the oceans hold a lot of our carbon dioxide. Once enough of the ocean has been evaporated, a lot of carbon dioxide will be released, which will make it hotter and hotter until the oceans have completely boiled away. Some astronomers do believe Venus, once upon a time, had oceans due to satellites finding rocks that appear similar to those found on Earth, which would need water to form. Venus probably lost water through photodissociation. When a photon from the sun impacts a water molecule, it forces the hydrogen and the two oxygens to separate. The hydrogen, being super speedy, escapes into space, and the resulting two oxygens end up bonding with a carbon atom, forming CO2. And we can take a look at how this works. So first we have our photon coming in, where they're breaking up the party. Hydrogen says peace out, goes off into space. We have our two oxygens left. They meet a lonely carbon, and they become friends forever, forming carbon dioxide. The surface of Venus has both high temperatures and high pressure. Spacecraft, Venera, and others have sent photos of Venus back to Earth, but they generally don't last more than an hour due to the high temperatures and pressure they can't survive. Most of the rocks we see on Venus are volcanic, and most of what astronomers know about the surface is from radar. Most of the surface is low, generally rolling plains, and there are two major highland regions, Ishtar and Aphrodite, which are both goddesses of love. They appear as raised land masses similar to terrestrial continents. Ishtar is about the size of Australia and is studded with volcanoes. The largest of these is 11 kilometers high off the plateau called Maxwell Montes. Aphrodite is about the size of South America and located near the equator of Venus. Combined, both masses take up about 8% of the surface. Volcanic landforms dominate the surface of Venus, and unique features such as peaks with immense flows, blisters of uplifted rock, dubbed pancake domes, which are lava domes but flat on top, and grids of faults. Due to high pressure and temperature and no water, the rock would need to melt at high temperatures than if there was water involved. Okay, so what this means is on Earth, you have temperatures that are super hot in the core, right? And in the mantle, when these temperatures are high enough to overcome the pressure, which would keep everything close enough to stay solid, you get liquid forming. But when you add water, that temperature actually needs to be less. And so without water, you're going to have a drier magma, which means that on Earth, we would have very steep volcanic peaks, which is what we see on Venus. Features on Venus indicate a young, active surface. Faulting, volcanoes, lack of impact craters. This leads scientists to estimate that the surface is probably only about 500 million years old. On Earth, we have plate tectonics, which allows our surface to remain unblemished and young. However, how is this working on Venus? We don't appear to have the same plate tectonics. There doesn't seem to be any convection. Hypothesis number 1. Volcanism is most likely a result of hot spot mantle plumes like Hawaii. However, it doesn't appear as if there is any current activity. The crust of Venus is thick, so might trap heat, making volcanism periodic. Heat leads to a slight melting of the lower crust, which leads to thinning and breaking, allowing magma to rise up, forming a volcano. Based on observations, scientists know there is fresh volcanic lava flows, and SO2 in the atmosphere may be due to volcanic gases being used. The second hypothesis is there is convection and a flowing mantle, like on Earth, but because the crust is so thick and the rock more rigid, you have a different behavior. This is why we would see crustal bulges as magma rises within the mantle. The crust would bulge, stretch, and weaken, forming volcanoes without the conveyor belt system like on Earth, which is subduction and volcano. When magma circulates back down, portions of the crust are pushed together, making it thicker, and crumple into regions like Ishtar and Aphrodite. It would explain the faults and may gradually erase features like impact craters due to the push and pull at the bottom of the crust. Which one do you think is better? Now let's move on to Mars. Mars is the red planet. We're going to get to why in a second. But there is evidence for a Martian atmosphere. It is visible with clouds of wind-blown dust, meaning there's sand dunes. And when you have wind coming, the atmosphere actually turns pink. So we know there's an atmosphere there. Spectra indicates that the atmosphere is 95% carbon dioxide, 3% nitrogen with traces of water and oxygen. This is similar to Venus, but a lot less dense. It is only 1% of Earth's. And the carbon dioxide is a greenhouse gas. Like we learned before with Venus, it should lead to a greenhouse effect, right? But we're not seeing that on Mars. And that's because it's a much weaker effect due to it being super duper thin. The lack of heat trapping and the distance from the sun makes Mars colder than Earth. At the equator, it's just above 0 degrees Celsius. And at night, it drops down to 180 Kelvin, an average of 210 Kelvin. The clouds themselves are frozen water and carbon dioxide that are pushed by winds. And the winds work the same as on Earth. They're mostly gentle during the southern summers. They become gales and cast huge dust storms, which make the atmosphere pink. The Coriolis effect leads to winds going parallel to the equator. Another thing that's present in the atmosphere is methane, but trace amounts due to the quick breakdown. But since there's some, it suggests that there must be a current source because methane breaks down extremely quickly. On Earth, our source is life. Yes, we make methane. Cows make methane. Cats make methane. Or geologic activity, i.e. volcanoes, degassing. And that means it may be the same on Mars. The atmosphere is too cold and thin for rain, but sometimes they have fog and frost in the winter, and they do get snow at the poles. Pressure on the surface borders the limit of possibility for liquid water. So water then exists as ice, meaning that ice on the poles is possible. It's also possible that water has been preserved below the surface as ice as well. The reason for pressure being at the boundary of water is because the stable liquid pressure is 0.6% of Earth's. atmosphere, and if you below that 0.6% of one atmosphere, you will go from a solid to a gas, like dry ice. On Mars, the pressure at the surface borders that limit, so it's possible, but because it's so cold, it stays as ice. Analysis shows that craters on Mars have not been eroded by rain significantly in 3 billion years. This leads to questions. Obviously, Mars had water once. It's there as frozen ice. It's below the surface. We're finding evidence of it in the soil. But where did it go? Why did the atmosphere get so thin? There's a few possibilities. One is if it was like Earth once upon a time. If Mars' atmosphere was denser in the past, the greenhouse effect would have made it much warmer. If it thinned, this would have caused the permanent ice age that we see now. Mars's gravity is actually quite weak. Over 1 to 2 billion years ago, it may have actually reduced in its ability to hold its own atmosphere, meaning that gas would have escaped. The surface would have reduced, sublimation of water and hydrogen would float into space, Mars would cool, and the remaining water becomes frozen and buried with dust. They think in the first 1 to 2 billion years is when Mars lost its atmosphere. And the reason for that has to do with its core. But let's talk about the surface first. We have put many a spacecraft into orbit around Mars to study its geology, atmosphere, density, etc. Rovers have been sent to the planet to get data, photos, and explore. Scientists have determined that the density of Mars to be quite low. The gravitational field indicates a metallic core with half the radius of the planet, a mantle, and a crust. Density indicates an iron core with a decent amount of sulfur. And based on the tidal effect by the sun, the core is still partially molten, i.e., it has a wobble. Evidence of ancient volcanism on the planet and indicates that it once upon a time had a much stronger magnetic field, and that it was a much more active planet. There is an enormous rift, which is dubbed the Valles Marianas, which is 4,000 kilometers long, 100 kilometers wide, and 10 kilometers deep at the equator. It would run the length of the US from California to Florida. The Grand Canyon is 1/10 of its length. Scientists believe the rift may have been the early stages of plate tectonics like the mid-ocean ridge. Elevation maps indicate that the higher elevations are in the south rather than the north, and the highest region on Mars is the Tharsis Bulge, which pretty much spans the equator, is the size of North America, and it's dotted with volcanic peaks. The Valles Marianas starts roughly in the center of it, and the largest volcano in the solar system is found there, on the edge of the bulge, Olympus Mons. It rises 26 kilometers above its surroundings. To give you reference, Mount Everest only rises 8.8 kilometers. The bulge and volcanoes indicate a geologically active Mars at one point. Tharsis, due to rising magma, means volcanism. Rise of the bulge led to the rift, and activity on Mars has ceased due to planetary cooling as it aged. This is supported by the amount of craters we can see that Mars is tectonically low in activity levels. So remember, we were talking about Venus having a pretty young-looking crust. Earth has a pretty young crust. And the fact that we can see all of these craters still means that it wasn't able to fix its surface. There was no subduction. There was no push and pull at the crust to erase any kind of scarring. So generally, there's not much going on in Mars anymore. Analysis of rocks showed evidence of water involvement. Found rocks with lumps like conglomerates, which when found on Earth, means that water happened. So you would have pebbles or rocks being eroded quite smooth by water and then glued together by some other geologic force. Usually it has silica of some sort. And we can actually see an example of that right here. This is a conglomerate. This is one we would have found on Earth in a riverbed or by the ocean even. We have found what look like layers of sediment, like at the bottom of the ocean, with ripple marks, and minerals that have chemical compositions indicating they were deposited in a salty lake or small ocean. This further supports a blue Mars. Other Martian features found look like rivers and gullies, indicating water flow. Some led from Great Depressions, which have evidence suggesting there were once lakes. Frozen and dried up deltas are found at the poles, and what appear to be frozen oceans under the dust. we have what appear to be ice rafts, which we see in our own Arctic seas. Frozen water at the poles is about 2 kilometers thick and would actually flood the planet if it melted. Examination of the surface indicates there were many lakes and a large northern ocean with deltas. Minerals found in such areas indicate that they were much wetter. For example, hematite. You need water. Hematite is a precipitation of iron that forms with water. So finding hematite on Mars means water must have existed there at one point. Here's an example of how it looks at the poles. It's really cool, huh? And here are some of the deltas that were found. And so scientists believe that oceans were present until about 3.5 billion years ago, when Mars probably lost its atmosphere. Not many believe that water remains, but below the surface it has probably frozen. Hydrogen has been detected in the top meter of soil, which probably came from the ice itself. So if we dug down far enough, we probably would find more ice. Big question. Why is Mars red? Easy answer. Iron oxide, or rust. As the planet is pretty windy and we can see gales and dust storms, this iron oxide surface layer has been spread all over the planet. So maybe at one point we were able to see the frozen oceans. Not anymore, due to this thick layer of rust dust that has essentially been just spread all over the planet. Now let's talk about some moons. Mars has 2 moons, Phobos and Deimos. Mars is the god of war, and Phobos and Deimos are actually the Greek gods of fear and anxiety. Deimos orbits close to the planet. It has Deimos is fear, Phobos is panic, not anxiety. It orbits close to the planet, and Deimos is so close it only takes 30 hours to orbit, which is 6 hours longer than the Martian day. From the Martian surface, it takes 2.5 days between the rise and set of the moon, because they're so close. Phobos is closer. It orbits in 1/4 of the Martian day, and because of its speed from the Martian perspective, it appears to rise in the west and set in the east. Tidal drag on Phobos will eventually cause it to crash into Mars, which, if you think about it, if we were to ever live on Mars, panic would set in eventually. Due to these unusual orbits, astronomers think the 2 moons are actually captured asteroids, although they could have been formed the same way our moon was, which is to have an impact and a piece to be thrown off into space. The moons are too small to have the mass to form spherical shapes, and hence their oblong formations. Now let's go ahead and move on to the outer solar system. The outer solar system is known as the Jovian planets, or Jupiter-like planets. These include Jupiter, Saturn, Uranus, and Neptune. These planets are also nicknamed the gas giants, although Uranus and Neptune are also known as the ice giants due to their distance in the system, allowing them to collect frozen methane and ammonia. Let's start with Jupiter. Jupiter is about 5 astronomical units from the Sun. It is the largest planet in our solar system. It is 11 times Earth's diameter and 300 times its mass. It has belts of clouds, both dark and light. It rotates every 9.9 hours, and due to its speed and rotation has caused it to flatten some, causing its equator to bulge slightly. The equator is 7% larger than the diameter from the pole to pole. The atmosphere is 90% hydrogen, 10% helium, with traces of methane, ammonia, and water. This has been additionally tested and proved by the probe from the Galileo spacecraft. The high temperatures internally drive strong convection currents in the outer layers, making Jupiter quite stormy. Winds can get up to 500 kilometers per hour, which is the speed of a tornado. Deep circulation makes weather very different from Earth. The Coriolis effect deflects winds in an interesting manner. Winds farther from the axis, going towards the equator, are deflected to the west, and winds closer to the axis, moving towards the poles, are deflected to the east and pushed into jet streams. These are visible as the cloud belts of dark or light bands. The gas between the jet streams gets swirled into vortexes, which are brightly colored. The most well-known of these is the brick red Great Red Spot, which is a huge storm that has been active for over 300 years. It's an increased pressure region rising 50 kilometers above its surroundings. Winds swirl 500 kilometers per hour, as fast as a tornado. As long as Jupiter continues to supply a steady source of heat, it may actually continue permanently. We can actually see flashes of lightning due to storms 1,000 kilometers across and rain of some sort, probably ammonia-based. There's our great red spot. The interior of Jupiter is very different from Earth. The average density is 1.3 kilograms per liter, which is slightly more dense than water, which is 1 kilogram per liter. This means the atmosphere must be very thick, and the bulk of the planet must be very light, with elements like hydrogen and helium making up most of the atmosphere. Based on gravitational pull, astronomers have determined that the core of Jupiter must be made of high-density material. As pressures increase, the further you move into Jupiter, gaseous molecules condense. So at about 10,000 kilometers below that cloud top, Jupiter has a sea of liquid hydrogen. The pressure here is 1 million times the surface of the Earth. None of our spacecraft would be able to handle this. Below the liquid hydrogen, pressure continues to increase, and so we get liquid metallic hydrogen, which is something that scientists on Earth have only been able to make in tiny pressurized chambers for less than a second. Liquid metallic hydrogen allows electric currents to move through it like metal. Close to the center of Jupiter, pressure is 100 million times greater than Earth. Liquid will be compressed to densities greater than such as rock. Astronomers assume Jupiter was created from the same material as the Sun, and would also assume to have heavy metals. These would have sunk to the core, forming a core of iron and rock. Jupiter actually emits more energy than it receives from the Sun, indicating it has a molten core. About 30,000 degrees Kelvin, 5 times hotter than ours. Even 10,000 kilometers in, the planet is about 5,000 Kelvin, which is about equal to our own core's temperature. Astronomers assume that the heat may be left over from its formation, and that additional heat may be created as the internal material settles down under its own weight, meaning that Jupiter is probably still shrinking, and that all of the gas giants may be. Therefore, its heat is generated from pressure as matter is condensed. Heat can also be generated by differentiation. Matter denser than hydrogen will continuously sink towards the core, including the helium in its atmosphere. How? Well, it can condense, as rain, and fall towards the core. Friction will then be created, which leads to heat, and as helium is a light material, it would not sink as fast as other denser materials such as iron, oxygen, nitrogen. So it might still be occurring. Now let's move on to Saturn. Interesting fun fact. Both Jupiter and Saturn outweigh the combined total of everything else in the solar system smaller than them. Saturn is 9.5 astronomical units from the Sun. It is the neighbor of Jupiter, though not as brightly colored. It is smaller than Jupiter, only 9.5 times Earth's diameter, and 100 times the mass. It appears dimmest and slow-moving in the night sky without a telescope. Saturn is the Roman name for Kronos, father of Jupiter and leader of the Titans. Jupiter banished Saturn and all the Titans to the darkest pit, the furthest from heaven. Bands of color are more subtle in variation than Jupiter. This may be due to the difference of temperature of the planets, as Jupiter's outer atmosphere is 160 degrees Kelvin, but Saturn's is only 130, which is cold enough for ammonia to condense, which will create that cloudy cover, really inhibiting us to see colors. It rotates one time for 10.7 hours. It is slower than Jupiter, but it actually has a greater equatorial bulge. Its equator is 10% larger than the pole-to-pole diameter. Saturn also has rings that are very, very, very apparent. Saturn is known for its rings. Like Jupiter, the temperature of Saturn is high enough to cause strong convection. Winds can also go up to 500 kilometers per hour. They are also directed by the Coriolis effect, forming jet streams in bands, east to west and west to east, just like Jupiter. The reversals are called wind shear. The atmosphere of Saturn appears calmer than Jupiter, but it is just as dynamic. There is an atmospheric haze obscuring storms thanks to ammonia, and also complex cloud banding of light and dark. It has had a large storm that was viewed by Cassini spacecraft in 2004, and the coloration of Saturn's banding comes from its temperature being low enough for ammonia to condense to clouds, veiling deeper layers of atmosphere. The makeup of Saturn's atmosphere is 96% hydrogen, 3.3% helium, with the rest being methane, ammonia, water, ethane, hydrogen deuteride, and varying percentages below 1%. The density of the planet is less than water, only about 0.7 kilograms per liter. The bulk of the planet is hydrogen, which is why we have such a low density. It does, in fact, have a similar internal structure to Jupiter, with a liquid hydrogen C and a liquid metallic hydrogen below that. The mass of the planet exerts great gravitational force on the material. The compression of the material leads to super high pressures. The density of the gas increases with depth, and Saturn bulges more than Jupiter because the mass is more concentrated towards the center than Jupiter. The core also probably is rock and iron, many times the mass of Earth, and enveloped by metallic hydrogen. Infrared measurements indicate Saturn also emits more energy than received from the Sun, and heat could be left over from planet formation. It could be generated by planetary settling, although slower compression, and slower differentiation of helium. Saturn is generating more heat than Jupiter, which is hypothesized to be from the lack of helium in the atmosphere and the temperature of the atmosphere, that more helium has been able to condense and sink to the interior than the interior of Jupiter. Let's talk about their magnetic fields. We're going to talk about both Saturn and Jupiter at the same time since they both have a metallic liquid hydrogen ocean. The convection of metallic liquid hydrogen combined with rapid rotation would lead to a pretty large magnetic field. This will be driven by the natural dynamo process, just like on Earth. Jupiter is going to have the strongest magnetic field of any planet in the solar system, 20,000 times that of Earth's. Saturn's is 500 times stronger than Earth's. Just like Earth's magnetic field forms the aurora borealis, incoming energetic particles also get directed to the upper atmosphere, where it will spiral towards the poles in Jupiter and Saturn, also forming auroras. And here's an example of what those auroras look like. Unlike Earth, moons and ring particles orbiting Jupiter and Saturn also contribute charged particles in addition to the ones from the Sun. In particular, charged particles from volcanically active Io create a strong aurora on Jupiter. A side effect of Jupiter's strong magnetic field is that it also generates radio waves. Now we're going to move on to Uranus and Neptune. These were the two unknown planets and weren't identified in ancient times. Uranus was discovered in 1781 by Sir William Herschel, and he originally named it for King George III, Georgium Sidus, George's star. Years later, astronomers decided the name should follow the pattern of Roman gods and was named Uranus for the father of Saturn. Neptune was discovered in 1846 based off of predictions by John Couch Adams and Urbain Le Verrier, stating Uranus wasn't following its expected orbit and that there was orbital perturbation. Based on size and direction of the perturbation, we were able to predict that the body would be found. And they found Neptune, and it was named for the god of the sea due to its beautiful deep blue color. The atmospheres of both planets are rich in hydrogen and helium, just like Jupiter and Saturn, but with greater amounts of methane. Uranus has 82.5% helium, 15.2% helium, and 2.3% methane. Neptune has 80% hydrogen, 15% helium, and 1.5% methane. Methane in the atmosphere is the reason for the blue hues of the planets. It absorbs red light and orange light from the sun, reflecting back blue and green. The haze of crystals of frozen methane is presented in Uranus and Neptune's atmosphere due to the outer atmosphere being cooler than Jupiter and Saturn. Uranus is 19 astronomical units from the sun, and its mean atmospheric temperature is 80 Kelvin. Neptune is 30 astronomical units from the sun, and its mean temperature is 75 Kelvin. To study the interior of these two planets, astronomers rely on their density and shape. Uranus has a density of 1.3 kilograms per liter, which is close to Jupiter, and Neptune has a density of 1.6 kilograms per liter. Both are greater than the density of water. Masses are similar, so Uranus and Neptune must compress matter in their interiors to a lesser degree than Jupiter, and therefore must have fewer lighter elements, such as hydrogen and helium, than the other gas giants. They didn't accumulate as much gas from the nebula when the solar system was forming, and so do not produce the extremely large pressures needed to liquefy hydrogen. The best hypotheses for density and the atmosphere composition is that the two planets contain a relatively high amount of water mixed with methane and ammonia surrounding a core of rock and iron. The water is probably several thousand kelvins due to atmospheric pressure. Uranus' gravitational field suggests that the planet may not be as differentiated as well as the other planets. The hypothesis is that the core contains less iron, which explains why it doesn't emit as much heat on its own as the other gas giants. Both planets rotate about the same rate, about 17 hours and 16 hours is 1 day. This does also produce a strong jet stream, creating vortexes. On Uranus, the methane haze hides the jet streams and vortexes, and on Neptune, we have a distinctive cloud belt system, with the Great Dark Spot. This giant storm, or vortex, is blue and about 13,000 kilometers across, which is half the size of the Great Red Spot. It is not as stable as Jupiter's. It was noticed in 1989 by Voyager 2, but in 1994 it had disappeared, but a smaller one had emerged in the opposite hemisphere. Neptune's winds are the highest in the solar system, at 2,200 kilometers per hour. It's stronger because it's hotter and the atmosphere is colder, leading to extreme convection. Both planets have tilted axes. Uranus's axis tilted, making its equator nearly perpendicular to its orbit, and the orbits of its moon, similarly tilted, rotate around its equator. So basically, it's sideways. The hypothesis is that Uranus was struck by a large planetesimal, resulting in a tilt and material making its moons. Due to the tilt, the seasons are off compared to the other planets. One hemisphere will see perpetual day and the other perpetual night in its 87-year orbit. The polar regions get more sun than the equator, and in 2007, Uranus's polar axis was perpendicular to the sun, allowing for the sun to shine directly on the equator. When observed with infrared telescopes, large storms were visible. Markings had been noticed in the atmosphere, and Uranus had a typical day-night variation. Magnetic fields around Uranus and Neptune are odd in orientations. Uranus is about 47 times that of Earth's, with Neptune being 25 times that of Earth's, making their fields between other gas giants and that of Earth. But both are tilted at large angles to the rotation axis and offset by a large distance from their centers. As both planets don't have liquid metallic hydrogen, it is assumed that a magnetic dynamo process occurs within the water layer. As to why the tilt, we're not really sure. It could be that irregular currents or localized currents are within certain spots, which cause it to be tilted that way. Moving on, satellite systems and rings. Let's start with our satellites, which are moons. The moons of the gas giants are all named for mythological figures. Almost all have regular orbits, circular, and the same direction as the planet rotation, indicating formation was a mini version of the solar system. Most of small moons recently found, however, do not follow planet rotation, indicating that they are probably captured bodies. Most satellites orbiting gas giants have a density that suggests they are a combination of ices and rocky materials peppered with craters and are tidally locked. Satellites with a density greater than 400 are spherical and less than 400 being irregularly shaped. Many of them are dark and appear to have thin layers on top of them, making them look rocky. Except some impact craters show white underneath, and densities of about 1 kilogram per liter indicate that they are probably most likely made of ice. Some of the medium-sized moons have smooth areas and faults like Saturn's moon, Enceladus, suggesting some internal heat and tectonic activity, causing melting on the surface and erasing impact craters. Heating would also allow dust to sink, making these moons brighter. Larger moons in some cases are dark and heavily cratered, indicating size doesn't make much of a difference. Uranus's moon, Miranda, the fifth largest moon, has faulting, and it has areas that are cratered like our moon, parallel grooves, and a set of cliffs larger than Mount Everest at 20 kilometers high. There are two hypotheses for this. 1, impacts broke it apart, but its gravity pulled it back together. 2, tectonic activity broke the surface into plates, like on Earth. All of the gas giants have rings. We just can't see them all. Saturn's is the most spectacular. Because of this, and that most of the rings aren't easily visible, astronomers thought only Saturn had rings. In 1610, Galileo noticed the rings on Saturn, except he thought they were handles, and so they must be satellites. Then they disappeared as Saturn moved, and the rings were perpendicular to Earth. A few years later, they reappeared, confusing all. It wasn't until 1659, when Christian Huygens saw the rings of Saturn were detached and encircling the planet, that it was realized to be rings, and at this point they thought they were solid. In 1857, James Clerk Maxwell mathematically determined that no materials could be strong enough to be a solid sheet of such a size, so it must in fact be particles. And it turns out, Saturn's rings are made up of a bunch of orbiting particles and bodies that rotate at appropriate velocities to the distance. The rings are wide, but very thin. The main system of rings extend 2 times the radius of Saturn, 136,000 kilometers. Some faint inner rings are closer to Saturn, and some faint outer rings are greater than 8 times the radius. The rings are thin enough to see stars through, and they're just a few hundred meters thick. The ring particles must be small, centimeters to meters, which has been determined through the echo of radar. Jupiter has the least substantial ring. It was discovered in 1979 by Voyager 1. Uranus and Neptune also have small sets of rings. The spectra indicate Saturn's ring particles are mostly water ice, but have different compositions. The darker means the more carbon compounds. Uranus also has carbon compound rings, and Saturn's rings are not uniform. There are gaps, the biggest being the Cassini division. This occurs where the ring particles orbit in half the time it takes for the moon Mimas to orbit. And this causes resonance, a relationship between their orbits, meaning any particle orbiting in the gap would receive a strong tug by Mimas every other orbit, resulting in a pull of particles from said gap, creating the division. Other gaps are due to spiral density waves, due to small moons orbiting within the rings, causing gravitational attraction on winged particles, generating these waves. And they form spirals as inner parts move faster than outer parts. The tight spirals cause the formation of thin rings, and when 2 moons on opposite sides of the ring occur, it's known as shepherding satellites, and they will deflect the ring particles into narrow streams between the 2 orbits. Dust from impacts on the moons and destroyed moons due to them reaching their Roche limit. And the Roche limit is when a moon is too close to its host. The gravity of the host then tears it apart. This is known as tidal force, and the point at which it becomes too large, resulting in moon destruction, is called the Roche limit, which is like the point of no return, and it's destroyed by its planet's gravity. So dust from impacts on moons and destroyed moons are what make up these rings. Now let's talk about our ice worlds, Pluto and our other dwarf planets. So we're going to start with the 4 largest moons of Jupiter, discovered by Galileo. Io is volcanically active due to being tidally locked with Jupiter and being gravitationally influenced by Europa. The closest moon to Jupiter is Io, and it has an elliptical orbit due to the influence of Jupiter's pull, where the moon is constantly being reshaped and its core is heated. The volcanic activity has pushed most of Io's water into space, and the major component of its eruptions is sulfur, giving its red, yellow, orange coloring. Europa is the smallest moon. It has many cracks and freckles. Its reddish coloring in and around indicate mineral-rich water coming to the surface, then freezing. It may be a result of volcanic activity, suggesting heat rising from the interior, melting the icy surface, which comes from deformation thanks to Jupiter and its neighbor, Ganymede. The density of 3 kilograms per liter indicates a rock iron core. Astrologists think there is flowing water underneath the ice surface, which may harbor life. Ganymede and Callisto both appear to be primarily ices. The grooved terrain of Ganymede suggests tectonic activity. Ice appears to surround the rock, mantle, and iron core. It has a magnetic field, so the core may be molten. It's suspected that there is a thick layer of water, either of which could generate electricity, or a magnetic sphere. Titan is Saturn's largest moon. It is also the largest moon in the solar system, with a diameter of 5,000 kilometers, making it bigger than Mercury. The atmosphere is dense and creates pressure comparable to that of Earth, but it is cold. It is 95 Kelvin. It has a mostly nitrogen atmosphere, not as much oxygen as Earth either. Astronomers think that methane or ethane may circulate the planet as rivers, lakes, evaporating, and raining on the surface. Hydrogen cyanide and methane are both present, which can create an amino acid that can actually create life. Triton is a moon of Neptune and is nearly as large as Europa. It rotates around Neptune backwards, and many think it's a captured protoplanet. It also has an atmosphere, but less dense than Titan's. Its features include wrinkles, craters, which some appear to be geysers of nitrogen, oxygen, and carbon compounds, and erupted material freezes and is deposited as dark mats on the ground. Pluto was discovered in 1930 by Clyde Tombaugh, and it is named for the god of the underworld. Originally, it was thought that Uranus and Neptune's orbits were being disturbed by another body, and based on the amount of supposed disturbance, this body must have been massive. It turns out there was not actually disturbance, and Pluto was actually found by accident. The mass of Pluto, determined in 1978 when Moon Charon, Bowman of Styx, was discovered, which is to be about 0.002 times the mass of Earth. It has a very thin atmosphere, and it is 39.5 astronomical units from the Sun. Its elliptical orbit is due to Neptune's gravitational pull. In 1992, the discovery of the Kuiper Belt and planets beyond Pluto demoted it from a planet in 2006. Pluto has also been discovered to have compounds and oceans, which is pretty cool. Now let's get on to some trans-Neptunian objects. There are more than 1,000 objects detected, the largest of which is Eris, the goddess of strife and discord. It is 27% more massive than Pluto. And because of TNOs, that term dwarf planet came about, which are planet-like bodies that have round shapes due to their own gravity, but are unable to clear their own path. TNO dwarfs are labeled as plutinoids, and classes amongst these bodies are plutinos, which have orbits similar to Pluto's, and there are several hundred of them. The current analysis shows that many of these dwarf planets have unusual characteristics and even orbiting moons. These include Sedna, being as red as Mars, and Haumea spinning so fast its equatorial bulge is nearly 2 times its pole-to-pole diameter. And that, ladies and gentlemen, is our lecture. I hope you guys enjoyed learning about our solar system, and I'll see you guys next time. Please remember, post all comments and questions in our comment section, and have a great day.